Alright, so today we're going to be talking about the relaxation method for solving Laplace's equation in one dimension. So why do we care about Laplace's equation? Well, we care about it for a multiple number of reasons. So in heat flow, whenever we want to find the steady state solution for a system, in other words, when partial u over partial t is 0, then that's whenever we end up with Laplace's equation, which gives us the steady state heat distribution of a system. Or in electrostatics, we might know the potential at the boundary of some surface, and we want to figure out the potential everywhere, and once we have the potential, we can get the electric field. So, in today's video, we're going to be considering a pretty simple problem, but it'll get more complicated as we go through this series, and throughout this series, we're going to need these approximations right here. If you've done numerical stuff with ODEs, then this probably looks familiar. If not, there's going to be a link in the description that goes into a lot of detail about these, but basically, we're going to be substituting these approximations everywhere where we see partial derivatives, and that's going to give us a method to figure out an approximate solution to the problem. And why do we care about numerical solutions? Well, the majority of the time, we'll be wanting to know the heat flow or heat distribution in some strange geometry or a very difficult to deal with forcing function. So we're not going to be able to solve analytically, so the only option we're left with is to figure out it numerically. Now, today, we're going to consider heat flow in an insulated rod. I say it's insulated on the sides so that no heat can flow outwards. So in other words, this right here is not allowed. And heat can only flow, in other words, heat can only flow in the rod itself, like this, laterally in the x direction. And we'll say at the very end of the rod, so this end of the rod, it's going to be held at some reference temperature. For simplicity, we'll call it 0, but in actual application, this would be some temperature, and the other side is going to be 1 unit higher. So you could say maybe this is like 20 degrees Celsius, and this is 21 degrees Celsius. It doesn't really matter what the exact values are, we're just using reference temperatures right here. And we want to figure out what the heat distribution in this rod is going to be with time. So, before we get started with the coding, we need to ask ourselves what we expect to happen. So, this could have a variety of different initial conditions. For example, the initial condition could look like this, or it could look like this. But regardless of the initial condition, we probably expect, as time goes forward, the heat will eventually, after some time, distribute itself evenly through the rod. So it'll increase linearly with x. Now, how are we going to do this? Well, we're going to use that finite difference approximation we talked about earlier. So we start off with the Laplace equation in one dimension, and then we substitute our finite difference approximation. Now, these subscripts right here mean we're going to chop our rod up into different pieces like this. So we're going to chop it up into tiny pieces like this, and the more pieces we chop it up into, it'll be a better approximation to the solution. So we'll say this is maybe I equals 0, and this place right here is I equals 1, I equals 2, and then maybe this will be I is equal to n. We're going to have n pieces. So after we plug in our finite difference approximation after doing some algebra, we see that the temperature at any point is going to be the average of its partners. So right here, the temperature right here is going to be the average of I0 and I2. Now, you could basically write out all these different equations, so you would have, U0 is given to you. It's the boundary condition. But for all your interior points, you could write out, like, U1 is equal to 0.5 U0 plus U2, and so on and so forth. And you could form a matrix with these and then solve that matrix. But what you would see, and I encourage you to do it, that matrix is going to consist mostly of zeros. And so it's faster to solve it by using something called the Method of Relaxation. And to solve something by relaxation, you basically do the following. So right here, we know what our boundary conditions are. So, in other words, we know U0, it was equal to 0, and we know UN is equal to 1. And so what we do is we chop up our rod into different pieces, and then for all these interior points, we're going to make an initial guess. We're going to it's a kind of reasonable guess. We'll just guess all these points are the average of the two boundary conditions. So in this particular example, we would make the initial guess that all these are 0.5. The temperature at all these is 0.5. And then what you do is you sweep through all these interior points and set them equal to the average of its neighbors. So, to start off this algorithm, so you would start right here, and you would say, alright, this position right here is going to be the average of this one, and this one right here. So in other words, it gets updated to 0.25. Now this one is going to do the same. It'll be the average of 0.25 and 0.5, and it's not, I don't know. I'm really bad at mental math, but, anyways, you get the idea. And then you go through all these points, and you basically do this until the solution converges. In other words, each time you go through, if your new guess doesn't change by that much, then you're starting to converge. And then you know you're done. So, like I said before, if you cut this into a lot of different pieces, then you'll see that the solution gets better and better the more pieces you add. And then eventually you should get something that looks like this. So just to show that, I'll actually show the code. So we're going to go over here, and then we see that indeed our solution does converge to the actual answer. And I hope you enjoyed this video. There will be a link in the description that has that ODE book, and it's going to have the code for this example. So I encourage you to look through that, and then I'll see you on the next video.